All right, hello everyone, and welcome to my channel. This is an educational channel, and we focus on great theories of everything from the ancient and recent past, things that you can hang your hat on because they offer answers to any questions that you might have. All-encompassing theories that will help you with your paradigm shift, also your awakening to 5D consciousness and the formation of your holistic worldview. Today is our 495th video on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson was an American engineer who lived in the 20th century. He died in 1990, but not before he put out 12 or 15, I don't know how many books, 50 articles, many lectures, and he, in 1959, proposed his two fundamental postulates about how the universe operated, and then from there he derived a theoretical universe about what his universe would look like if his postulates were correct. And then he compares his theoretical universe with the measured universe of the mainstream scientists. And he does it in books like the one we've got in front of us right now called Basic Properties of Matter, which is on chemistry. Larson arrives at equations for many of the basic properties of matter, like the melting point and such like. And then he compares his results with the measured results that the scientists had put together in their laboratory experiments and compiled in their tables. We are on chapter 15 of this book that is called Electrical Storage. And this is an interesting chapter because even though I am firmly in support of Larson's work and what he's done, he's kind of botching some things here in this chapter, in my opinion, with some incorrect attributions of units for, in particular, the farad, which is the unit of capacitance. And we're going to continue to go over that here. Now, if you want to get a thorough, or at least more thorough, rundown of Larson's theory itself, his fundamental postulates and their ramifications, you want to watch any of my first 474 videos on this subject. I go into it for at least 20 minutes or something, and then you probably want to come back and watch this video. In this presentation, I will basically assume that you have some working knowledge of the reciprocal system and how it operates. I will articulate Larson's two fundamental postulates and a couple basics here, but Larson's first postulate, Larson is the reciprocal system of theory, also known as the universe of motion. One of the few scientists to propose motion as the constituent of the universe. His first postulate reads that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with two reciprocal aspects, space and time. Okay, so the universe is made out of motion. Motion is the relationship between space and time, which sets up a generalized reciprocal relationship between space and time. Space and time do not have any existence of their own. They only exist together in motion. Space, time, and motion exist in 3 dimensions. Space, time, and motion exist only in discrete units. And when Larson refers to motion, he's referring to what he calls scalar motion. This is a motion that has a magnitude, but it has no specific direction. So it is a more generalized kind of motion that you can envision using a balloon that you put dots on, If you blow up the balloon, all the dots are moving away from each other. Each dot is moving in every direction away from every other dot, no specific direction. And if you contract that balloon, all of the dots will be moving toward each other. Every dot will be moving inward toward each other dot in all directions. And Larson refers to the outward motion as the progression, and that inward motion as gravitation. And these are the two major kind of motions in the universe. And the progression is really our potential or the source. This is the empty universe. And then manifestation comes from basically like reversing that motion of the outward progression to inward gravitation, which implies matter, aggregates of matter, and so on. Okay, now in Larson's system, the discrete unit postulate, motion is basically a fraction with space or time as the numerator and time or space as the denominator, such as speed. The car is moving 15 miles an hour. 15 miles of space in 1 hour of time. Space over time is speed. All of our scientific phenomena are forms of motion, and they all can be described in space-time terms, such as matter. Matter is time to the third power over space to the third power. Pressure is time over space to the fourth power. Energy is time over space. Force is time over space squared. Acceleration is space over time squared, and so on and so forth. And so that's where Larson finds himself here in this chapter, where he attributes capacitance, electrical capacitance, to the units of space. And it causes him to kind of do somersaults with his theory, because I believe this is an incorrect attribution, and this was corrected by one of his associates at a later time, and they proposed that capacitance is actually S to the third over T. And I don't know if Larson was aware of this or if he thought of it. I'm guessing that he probably did, but he rejected it because of the discrete unit postulate. He believes that, I believe that if you're using a fraction, the exponent in the numerator needs to be equal to or smaller than the exponent in the denominator. And I don't understand why that defies the discrete unit postulate. And so I have to side on the side of Dave, the other guy who came up with the S to the third over T attribution for capacitance, because it works out. Whereas Larson ends up having to do the contortion of coming up with a capital Q coulombs for one for charge and one for uncharged, a lowercase q. And while if you use the S to the third over T attribution for capacitance, everything just works out, cleanly. So this is what Larson is doing here in chapter 15. Okay, that's the place that we're at right here from the text. It says in textbook and then correct. So two different columns. So in textbook, so he's criticizing the textbooks for having the wrong, because Larson feels like with his S attribution that he's corrected things, but he's only corrected them if he has a lowercase q and an uppercase q for coulombs, so two different coulombs. Now this does make a little bit of sense, because in Larson's system we have both a charged and an uncharged electron. The normal electron is uncharged, and it is a rotating unit of space with the units of space, S. And the charged electron is, well, it's a charge on an electron. In legacy science, a charge basically implies an electron. So a charge is an electron on something else. But in Larson's system, a charge is just like everything else. It is a kind of motion. And a charge is a rotational vibration. It's rotating, but it's also vibrating. In Larson's system, there's really 4 kinds of motion: translation, vibration, rotation, and rotational vibration. And so a charge is a rotational vibration, and an electron can take a charge to become a charged electron, units of T over S, or energy or charge. And so we've got a charged electron and an uncharged electron, S and T over S. And so I think that kind of gives Larson some impetus to think that it's legitimate to have a lowercase q for coulombs, and which is S, and an uppercase q for coulombs, which is T over S. And so he thinks that he's solved his problems here. So in textbook, we have the equation capital QV, so that is T over S times T over S squared. That's voltage. V is voltage. Voltage is a force, T over S squared. And we get T to the second over S to the second. But he doesn't say what that equals. I don't know what this presentation is exactly. This isn't really instructive. Then he says the correct attribution is actually lowercase q times V, because apparently QV equals E. QV equals the energy. And so when you use the lowercase q, then you have S times T over S squared equals T over S. And that is the units of energy. And then the next one, we're again shooting for units of energy. Q, capital Q in the textbook, capital Q over capacitance times, I guess this is the derivative of Q. It's just dq, or maybe that's distance Q. So he ends up with T over S, or the textbook ends up with T over S times 1 over S, times T over S, another capital Q, equals T squared over S to the third. But if you do it correctly, then you end up with capital Q over C D lowercase q. And that works out correctly. Well, so he's got this for a few different lines, and here comes the explanations. The error in this series of expressions was introduced at the start of the theoretical development by a faulty definition of voltage. As indicated earlier, the volt is defined as 1 joule per coulomb. But because of the lack of distinction between charge and quantity in current practice, it has been assumed that the coulomb entering into this definition is the coulomb of charge, symbol capital Q. In fact, as brought out in the previous discussion, the coulomb that enters into the energy equation is the coulomb of quantity, which we are denoting by the symbol lowercase q. The energy equation, then, is not W equals capital QV, but W, or work, which is energy. Work equals lowercase q times V. The correct terms and dimensions corresponding to those in the first two columns of the tabulation are shown in columns 3 and 4. Here, the term capital Q is in the first two expressions, and the term CV, which was substituted for Q in the last two, have been replaced by the correct term lowercase q. As indicated in the tabulation, this brings all four expressions into agreement with the correct space-time dimensions, T over S of energy. The purely numerical terms in all of these expressions were omitted from the tabulation as they have no bearing on the dimensional situation. When the full capacity of the capacitor at the existing voltage is reached, the opposing forces arrive at an equilibrium, and the flow of electrons into the capacitor ceases. Just what happens while the capacitor is filling or discharging is something that the theorists have found very difficult to explain. Maxwell found the concept of a displacement current essential for completing his mathematical treatment of magnetism, but he did not regard it as a real current. Quote, "This displacement does not amount to a current," he says, but, continuing, "it is the commencement of a current," end quote. He describes the displacement as, quote, "a kind of elastic yielding to the action of a force," end quote. Present-day theorists find this explanation unacceptable because they have discarded the ether that was fashionable in Maxwell's day and consequently have nothing that can yield where the plates of a capacitor are separated by a vacuum. The present tendency is to regard the displacement as some kind of a modification of the electromagnetic field. But the nature of the hypothetical modification is vague, as might be expected in view of the lack of any clear understanding of the nature of the field itself. As one textbook puts it, quote, "The displacement current is in some ways the most abstract concept mentioned in this book so far," end quote. Another author states the case in these words, quote, "If one defines current as a transport of charge, the term displacement current is certainly a misnomer when applied to a vacuum where no charges exist. If, however, current is defined in terms of the magnetic fields it produces, the expression is legitimate," end quote. The problem arises from the fact that while the physical observations and the mathematical analysis indicate that a current is flowing into the space between the plates of the capacitor when that space is a vacuum, as well as when it is occupied by a dielectric, such a current flow is not possible if the entities whose movement constitutes the current are charged electrons, as currently assumed. As stated in the foregoing quotation, there are no charges in a vacuum. This impasse between theory and observation that now prevails is another of the many items of evidence showing that the electric current is not a movement of charged particles. Our analysis shows that the electrons do, in fact, flow into the spatial equivalent of the time interval between the plates of the capacitor, but that these electrons are not charged and are unobservable in what is called a vacuum. Aside from being only transient, this displacement current is essentially equivalent to any other electric current. The additional units of space, electrons, forced into the time, the equivalent space, interval between the plates. Now, equivalent space is basically the, we do not see time. we only see space. But if something is in time, we see its reciprocal in space. That's just one of the concepts of the reciprocal system. Equivalent space has a few different characteristics. It's a second power entity primarily. And but we don't see time because we're anchored to a spatial reference system here in the material sector. And so that's what he means when he says equivalent space. The additional units of space, or the electrons, are forced into the time. And time is what occurs inside a unit of space. Because if you don't have a full unit of space, then you do not have space because of the discrete unit postulate. Space and time and motion have to come in only discrete units. And so if you don't have a full unit, which in the case of space is about 2/millionths of an inch, if you don't have a full unit of space, then you don't have space at all, and you only have time. And so if two particles approach each other to 1 unit of space, they cannot move any closer together in space because you can't get less than 1 unit of space. So instead they move outward in time, which is the equivalent of moving inward in space by the reciprocal postulate. So that's what's going on here. So the additional units of space, electrons, forced into the time equivalent space interval between the plates increase the total space content. This can be demonstrated experimentally if we introduce a dielectric liquid between the plates. As the increase in the amount of space decreases the internal pressure, the force per unit area due to the weight of the liquid. For this purpose, we may consider a system in which 2 parallel plates are partially immersed in a tank of oil, and so arranged that the 3 sections into which the tank is divided by the plates are open to each other only at the bottom of the tank. If we now connect the plates to a battery with an effective voltage, the liquid level rises in the section between the plates. From the foregoing explanation, it is evident that the voltage difference has reduced the pressure in the oil. The oil level has then risen to the point where the weight of the oil above the free surface balances the negative increment due to the voltage differential. Because accepted theory requires the displacement current, so-called, to behave like an electric current without being a current, conventional science has had great difficulty in ascertaining just what the displacement actually is. It is an essential element in Maxwell's formulations, but some present-day authors regard it as superfluous. All the physics of dielectrics could be discussed without ever bringing in the displacement vector, says Arthur Kipp. One of the principal factors contributing to this uncertainty as to its status is that the displacement is customarily defined and treated in electrostatic terms, whereas it is actually a manifestation of current electricity. In Maxwell's equation for the displacement current, the current density, 1 over s to the second power, and the time derivative of the displacement, capital D over dt, or the derivative of d, are additive, and are therefore terms of an equivalent nature. That is, they have the same dimensions. The space-time dimensions of current density are S over T times 1 over S squared equals 1 over ST. The dimensions of D, the displacement, are then 1 over ST times T equals 1 over T. Its place in the capacitance picture is then evident. In the storage process, units of space, uncharged electrons, are forced into the surrounding equivalent space, that is, the spatial equivalent of time. And this inverse space, 1 over S, becomes one of the significant quantities with which we must deal. Now, I'm wondering, it doesn't appear as if capacitance appears in this equation, and because he's just arriving at the displacement at the current density and then the displacement, and so he doesn't incorporate his S as opposed to the S cubed over 3. I mean S cubed over T. So I don't think that this is not a. He's saying that it is the inverse of. No, he doesn't. He doesn't say it's the inverse of capacitance. He says it's the inverse of space, inverse of electrons. So I think he's still on firm ground there. I think he only gets off track when he starts attributing the units of capacitance as space as opposed to the units of S to the third over T, which he didn't do there. So continuing on, in the customary electrostatic treatment of the displacement, it is defined as D equals, I believe that lowercase, middle case E is permeability, no, permittivity, and the O is free space, and then the capital E is the electric field intensity. So D displacement equals EOE. I don't know if doesn't look like a Greek letter to me. I'm not sure what it is, but regardless, it stands for permittivity of free space. Okay, where E is the electric field intensity, which is an electrostatic concept, and EO is the permittivity of free space. Since the dimensions of capital E are T over S to the third, which incidentally is the inverse of the capacitance, or at least Dave's attribution of the capacitance. And we have now found those of D to be 1 over S. The space-time dimensions of permittivity are 1 over S times S to the third over T, which is just the inverse of the electric field intensity. So he actually is multiplying it here by the capacitance without recognizing that that's what he's doing, and he ends up with S squared over T for permittivity. Now, he doesn't seem to have a problem here with the discrete unit postulate in attributing permittivity to be S squared over T. Then he says, in current practice, however, the permittivity is expressed in farads per meter. This makes it dimensionless, since both the farad and the meter are units of space. We are thus faced with a conflict between the dimensional definition of permittivity expressed in the conventional unit and the definition derived from Maxwell's relations, a definition that is consistent with the dimensions of displacement. The relation between the two in space-time terms, which is S squared over T, which would fit perfectly with Dave's farad being S to the third over T over S, shows where the difference originates, as this is the relation of the unit of electric current, S, to the electrostatic unit, T over S. The farad per meter is an electrostatic unit, while the S squared over T dimensions for permittivity relate this quantity to the electric current system. I don't see, why would the farad per meter be an electrostatic unit? The farad and capacitance is uncharged, and the farad itself is the units of S. So how could it possibly be an electrostatic unit? Unfortunately, I know very little about this topic, and I'm definitely not a chemist, and I'm not don't know anything about electricity, but just doesn't make any sense to me. And you may wonder why I even care so much and why we're going over this kind of arcane subject here. But the answer to that is that the reciprocal system is a generalized theory. And so if you understand how Larson does electricity or chemistry in general, then you can also apply that to any other subject. Larson uses the same principles to study chemistry that he does to study physics and astrophysics and economics and religion and philosophy. These are all intertwined in Larson's system. So, you know, it's important to study as many different subjects as possible and see the connections between them, see the analogies between them, see how he treats all these different things and figure out the links, and then you can start to get a bigger picture. And so that's why I'm concentrating here on the chemistry, not for the sake of learning chemistry, but for the sake of seeing the whole picture and being able to apply these concepts in other aspects. For example, you just take like something like alchemy. You know, Larson in earlier chapters of this book went over, you know, solid, liquid, vapor, and gas, you know, where the melting point is, how you determine the melting point, and so on. Well, solid, liquid, vapor, and gas is nothing but earth, air, fire, and water, or earth, water, fire, and air. And this is alchemy. So you want to understand these things. Anyway, thanks for tuning in today. We'll get back with this tomorrow. Have a great day.